Okay, these are going to be the inquiry questions for the inclined planes inquiry. In part one, we had a long white inclined plane and we just tried to set the angle so that the object would go down at a constant velocity, because at that constant velocity, that's an easy way to figure out what mu is between the two surfaces. So we're going to answer, there's 3 inquiry questions for that part 1. So part 1 says, draw an FBD that will derive the simple equation for mu if an object moves down an inclined plane at a constant velocity. Okay, so we have an inclined plane. We have an object on here, and we have the weight which goes straight down. Of course, we're going to resolve into a component going in like this, and a component going down like this. So this is the weight cosine of the angle of the inclined plane. And this is the weight sine of the angle of the inclined plane. We have a normal force going up like this. And we have friction force going back like this. Okay, so if this goes down at a constant velocity, we increase the angle till it's going down at a constant velocity. That means 0 net force. And we know that the weight sine of theta needs to equal friction force. And that means the weight sine of theta equals, and friction force, if you remember, is mu normal force. Okay. And in this case, normal force is equal to the weight cosine theta. So there's your friction, and we can put that in for this. So that'd be mu weight cosine theta. If you solve for mu, you have weight sine theta over weight cosine theta. Weights cancel, and sine over cosine is tangent of theta. So an easy way to figure out mu, it's equal to the tangent of the angle of the inclined plane at which an object goes down at a constant rate. So you can't just always take the tangent of the angle. You can't just always do that to get mu. You can only take tangent of the angle to get mu if the object is actually going down the inclined plane at a constant rate. So that's the answer to question number 1 for the inquiry questions. That's how you would determine mu. So in this inquiry, we figured out the angle at which the object was going down to constant velocity, and then all we had to do is take tangent of that angle, and we had mu for that problem. Okay, number 2 says, draw the FBD and derive an equation for acceleration down an inclined plane. Okay, so this time an acceleration down an inclined plane. So again, we'll have our inclined plane. We have an object here. We have Fn. We have the weight component going down. It would be W cosine of theta. Here's theta. Going down, we have W sine of theta. And upwards, we have friction. But if we know if it's accelerating down, that this friction is not going to be as much. Not going to be as much. Okay. So it's accelerating. That means there's an F net. There's an F net, which of course equals mass times acceleration. And the net force would be this one, subtract this one. So we're going to have W sine of theta minus friction should equal our mass times our acceleration. So then the W is, the weight is mass times gravity. So we'd have mg sine of theta minus, and what's friction? Friction is mu Fn. And in this case, friction would equal mu, and Fn would be W cosine theta. And again, W is mg cosine theta. So that can go in for our friction. So minus mu mg cosine theta equals ma. And I can cancel out a mass out of every one of these and have an acceleration equation down an inclined plane under its own weight would be g sine of theta minus mu g cosine theta. So there's an equation for acceleration down an inclined plane that does have friction. And we were going to increase the angle in that first inquiry to 20 degrees so the block accelerates. And then we were going to do a comparison there to see if we get the same acceleration rate that we measured in the incline. We also went below 10 degrees so that, and we have to give it a little push so that we get kind of a negative acceleration. We're going to try to calculate that out as well. Okay, and then question 3 says, what is the acceleration rate down a 30-degree ramp with a mu of 0.310? So that's number 3. We can solve that over here. So our equation is A equals G sine theta minus mu G cosine theta. So the acceleration would be 9.81 times the sine of 30 minus mu is 0.310 times 9.81 times the cosine of 30, and that'll be my acceleration rate. So 9.81 times 30 sine minus 0.310 times 9.81 times 30 cosine equals, I get an acceleration of 2.27 meters per second squared down the inclined plane. That should be the answer for that one. 2.3, I believe, is correct. Okay, so that's part 1. All right, part 2. Part 2. Need another piece of paper here. Okay, so for part 2, we did 3 different things, and we need to draw the FBDs for all 3 of them. So in part 1, we were pulling parallel with a constant velocity. So part 1, you'd have this, and we have FG going down like this. You'd have Fn should be equal. You have a pull force this way, and it was going at a constant velocity. So we should have a friction force going back, which should be equal. So that's the FBD for part 1. Part 2, we were pulling at an angle, also with a constant velocity. So we have the same kind of situation. FG, we have Fn equal and opposite FG. But in this case, we're going to have we're going to be pulling up at an angle, F pull, at some angle. We have friction going back this way. Now what we're going to do with this one is we resolve this F pull into a force going over and a force going up. Okay, we'll call this F vertical, we'll say. Okay, now this is F horizontal, and what we know is that this force needs to be equal to the friction. So I'm going to make this out here a little bit longer. I know that that needs to be equal because it's constant velocity. This would be F pull times the cosine of theta, and this would be F pull times the sine of theta. Sorry, I should put that all in one thing. Okay, and that would be the FBD for number 2. Number 3, we're pulling up an incline with constant velocity. So we have an inclined plane, theta. Here's our object. We're pulling up, so there's F pull. We have Fn going up like this. We have down, we have mg cosine of theta. And then down this way, we'd have mg sine of theta. And we would also, going down, have a friction force, and that'd be equal to mu Fn, and Fn is mg cosine of theta, so it'd be mu mg cosine theta. So this F pull needs to equal this and this if we're going up at a constant velocity. So those are the 3 FBDs for part 2 that we had to draw. And then question 2 says, what force is required to pull a 100 Newton weight up a 60-degree ramp with a mu of 0.130? So if we look at this third problem, this third FBD again here, we got an equation for F pull. F pull should equal both of these forces. So, it gives it the weight is 100 Newtons. So I don't have to do mg. I can do weight sine of theta plus mu weight cosine theta. So the F pull is going to be the weight 100 times the sine of the angle, which was 60, plus mu, which is 0.130, times the weight 100 times cosine of 60 should give me my pull force. So I have 100 times 60 sine plus 0.130 times 100 times 60 cosine equals, and I get an F pull, a pull force of 93.1 newtons. And if you check that drop down in the inquiry, that should be correct. So those are all of your inquiry things that you need to have. In this particular year, when I made this video, we had COVID lockdown, so we didn't actually get to do the actual pulling on the inclined planes. So this is all you need to have for the inquiry for this particular year. And any other year, you would need the actual results from the inquiry. Okay, hope that helps.